Today's demonstration is divided into two main parts, the user console and the admin console. The user console is designed for database administrators. You can create and manage database instances and view their running status, logs, and monitoring information. The admin console is for KubeBlocks, enterprise administrators, used to manage users and environments. An environment specifically refers to a Kubernetes cluster. Today we will focus on the features of the user console, using MySQL as our example. First, let's explore the user console. After logging in, you'll see a dashboard that displays all instances, backups, and alerts for your current organization. The current organization is named APEC Cloud Demo. You can click on the top right to view organization details. As this is a new organization, there are currently no instances, backups, or alert messages. The left-hand menu bar offers rich content, including database clusters, parameters, backups, and alerts, which we will introduce one by one shortly. Now, let's start with creating a database cluster. Click Create Cluster, and you'll see that KubeBlocks Enterprise supports various databases, including PostgreSQL, MySQL, Oracle, SQL Server, ClickHouse, Redis, MongoDB, and more. Today, we will create a MySQL cluster as an example. On the Cluster Creation Details page, you'll see the following configuration sections. The first section is basic information. First, choose the cluster topology, standalone or replication. Then, 4 major versions. KubeBlocks supports MySQL 5.7, 8.0, and 8.4, and then choose 8.0, 39 as the minor version. The second step is to select the availability zone. Since there's only one AZ in this demo environment, you may choose any if multiple availability zones are configured. We could distribute instances of the cluster across multiple AZs. The third part is resource configuration. We provide 2 types of specifications by default, general and exclusive. The main difference lies in their overcommit ratio. General specifications typically have a CPU overcommit ratio of 2 to 10 times, but memory is not overcommitted. Exclusive specifications mean neither CPU nor memory is overcommitted, primarily used for critical business scenarios. Each specification type includes predefined standard specifications, suit different workload demands. Next, we select Ape Localhost Path as the storage class. Developed by Ape, it is suitable for local disk scenarios. Additionally, you'll see many other storage classes to choose from. It's important to note that the predefined specifications seen here, including the overcommit ratio for each type and which storage classes are supported, are configured by the administrator. We can select the number of MySQL instances, ranging from 2 to 5. Then choose to use the default parameter template and specify the time zone, since time zone is one of the most commonly used parameters during user creation. We've placed it on the creation page for convenience. The fourth section is backup configuration. We can enable automatic backup. Set the backup retention period to 7 days, the full backup cycle to 2 a.m. daily, and enable continuous log backup for point-time recovery, PITR. Furthermore, we also support incremental backups. If incremental backup is checked, the default configuration for incremental backup runtime is 2 a.m. daily. At this point, the system will suggest that you can appropriately adjust the full backup cycle. For example, setting it to run full backups at 2 a.m. every Sunday. Let's review the backup configuration. Default retention for 7 days. full backup at 2 a.m. every Sunday, incremental backup at 2 a.m. daily, and continuous log backup enabled for point-in-time recovery. In addition, we can also set deletion protection to prevent accidental deletion of clusters by users. The right side of the page displays a cluster overview, including the cluster name, engine type, version, specification information. Click Create Cluster. Here you'll see the cluster's basic information, including its topology resources version. In the topology section, we can see that the current cluster is being created. It will create 2 instances, one primary and one secondary instance, which will take approximately 1 minute. The cluster will become running and start providing services only after both instances are in a running state and assume their expected roles. Currently, MySQLO is the primary instance. We provide a series of common operations here: switchover, volume expansion, vertical scaling, horizontal scaling, and restart. Next, we will introduce the usage of each operation step by step. Switchover is commonly used in proactive maintenance scenarios, such as switching between primary and secondary instances. After clicking Save, an Ops Request task banner will appear at the top of the page, indicating the task currently being executed. A few seconds later, we see that the switchover was successful, and MySQL1 has become the current primary node. Volume expansion is primarily used to expand storage space. Here, we will expand the storage space from 20 GB to 30 GB. After clicking Save, an Ops Request task prompt will appear at the top of the page again. The change will succeed in a few seconds, and you can see the updated information in the instance list. Vertical scaling refers to changing CPU and memory specifications. We can change it to 2C4G. After clicking Save, the cluster status changes to updating, and it will become running in about a few seconds. Since KubeBlocks supports in-place vertical scaling, this specification change does not require a pod restart, hence there is no downtime. In case of increased business load, MySQL can quickly scale up to respond to demands. Now let's look at horizontal scaling. We will increase the number of instances from 2 to 3. And you can see a new instance, MySQL-2, has been added, and the cluster status has changed too. Updating. Click the Ops Request task operation at the top to view specific information. This is an operation audit page, which records all operations we've performed on the cluster from start to present. Let's check the details of horizontal scaling. It records when and by whom it was initiated. Clicking Details shows information for each step. And here it indicates that the current operation was successful. We return to the cluster status page and can see that the current operation is completed. The cluster currently has one primary instance and two secondary instances. Since monitoring metrics has not yet been collected, the primary-secondary replication delay information is not displayed. During horizontal scaling, MySQL will restore data from a specified node via extrabop and then establish replication relationships, which may cause a brief delay. We can see that the current replication delay is 9 seconds. This is because it was just created, and the data has not been fully synchronized yet. As it begins to synchronize data, the replication delay will gradually decrease. After a short wait, it now shows 0 seconds, indicating that the primary and secondary instances are fully synchronized. The current cluster has 3 instances, with miscal1 as the primary instance. KubeBlocks performs operations based on roles, not pod ordinals. When we click Restart, the system will first restart the 2 secondary instances and then restart the primary instance. And we will observe the restart order follows roles as expected, secondaries first, primary last. When we are going to restart miscal1, a failover will occur. You can see that MySQL0 becomes the new primary node soon, and miscal1 is being restarted now, and the entire restart process takes approximately a few minutes. Next, we will introduce how applications can access the database. Here, we provide 2 ways: through expose private endpoint within VPC, or expose public endpoint. KubeBlocks offers 2 different service types: read-write and read-only. We choose read-write. After clicking, an expose ops task will appear at the top of the page. After it runs successfully, we can click to view the private endpoint, which will display connection information that applications can use to connect to the database. Similarly, the public endpoint also provides read-write and read-only options, which we will not go into detail here. Next, let's start with observability, covering metrics, logs, and SQL audits. Click Metrics and you'll see that we provide 3 sub-items: Cluster Monitor, Pod Resource Monitor, and Alert Setting. First, let's look at Cluster Monitor. Here, we can check database metrics at instance dimensions. You can customize the time range or select the past period. On the monitoring dashboard, we provide rich panels such as an overview, query-related monitoring, replication lag, current network traffic information, locks, file and table information, etc. Both the monitoring dashboard and metrics are user-definable. Resource Monitor mainly displays the resource usage of the current pod, including CPU memory storage and network. Alert Setting mainly includes alarm rules and notification policy, which we will introduce later. Next, let's look at logs. Logs are mainly divided into running logs, slow query logs, and HHL logs. Running logs can be viewed by different instances, and you can also select a custom range to view logs. By default, log information is retained for 7 days, but this retention time is configurable. Slow query logs can be used for performance, problem diagnosis, and SQL optimization, recording SQL statements that execute longer than a threshold. HA logs mainly display high availability log information, primarily of 2 types. One is switchover information, and the other is instance failover information. We just performed a switchover, and a failover occurred during the restart. So there will be 2 records showing specific information here. This information helps us diagnose the health of the cluster. Database audit logs meticulously record all access operations and modification activities performed on the database. Similarly, we can also select different times to query the audit information for the current instance. Now let's look at backup and restore. Click the backup page, and you'll see the current, default backup policy information, including the backup repository, whether automatic backup is enabled, the default backup retention period, whether PITR is enabled, and so on. To make changes, you can click the Backup Policy button above to adjust backup settings. We also provide a backup encryption feature. If you want to encrypt backups, you can check the box. After the cluster is created, an initial backup will be created first. You can see that it will display the backup execution time, backup size, backup status, and other information. Since we haven't reached the scheduled incremental backup time yet, there's no incremental backup here. We check the continuous backup information, click its details, and can see some specific information about the current backup, including the restore point information. The restore jobs list is empty because we haven't performed any backup restorations yet. In addition to scheduled backups, we can also initiate an end-to-end backup. For example, here we initiate a full backup and view backup status. To get more detailed information of the backup, you can click Details, and the panel has more information, including its start time, duration, size, and status. Here it shows that the backup is completed, and it can display the start and end times of the backup. With a backup, we can also restore a cluster. There are 2 main ways to restore: by backup set or by point-time backup. Here we see the 2 full backups from earlier. Point-in-time restore will display an effective time within the current continuous backup, and we can restore to any point in this time range. Here we demonstrate restoring by backup set. Click the desired backup set, and other options can use default values. Unlike creation, when restoring a cluster, you'll see a restore operation task, and the cluster status will be restoring instead of creating. Restoration is mainly divided into 3 steps: restoring data, creating the cluster, and then calling post-ready tasks. Since the backup set is small, the restoration takes approximately 1 to 2 minutes. We see the cluster being created. When all pods are ready with expected roles, a post-ready task will also be scheduled to handle some post-restoration steps, such as deleting temporary files. When all tasks are completed, the cluster status will become running. Let's look at the restore information. You can see that the original cluster's restore history is empty because it has not undergone any backup restoration. But if we look at the cluster that was just restored from backup and check its restore jobs, you can see there are 2 restore jobs, and we can expand one of them to view its details. Which shows from which backup it was restored, the execution time, and which jobs executed it. Next, let's look at parameter changes and management. All available parameters will be displayed here. For example, if we search for the max connections parameter, hover on the question mark to get a description. And it also describes whether the change requires reboot to take effect. We change it to 1000 and click Save. You can see that we changed this value from 668 to 1000, and it doesn't require a restart. Click Save. We can see that the change was successful. You can view the configuration change history, which records the parameters changes, the owner of the change, and which configuration file it affected. Additionally, we can export the currently used parameters as a parameter template. For different types of workloads, we need to adjust different parameters. For example, we usually prepare high-performance templates and high-availability templates for MySQL, but these predefined templates may not meet all needs. Therefore, custom parameter templates are very useful. Here we can export the current parameter list as a parameter template for future use. Add a name, description, and then click Save. After saving, when we create a MySQL cluster next time, we can reuse this parameter template. We return to the home page and click the Parameters menu. You can see both custom and default templates here. In the custom templates, you can see the parameter template we just created. We search for max connections and see that its value is indeed 1000. Next, we can use this template when creating a cluster. Click Create Cluster to create a MySQL cluster in this environment. Use default values for these configuration items. In the Parameters template section, we choose to apply the custom template we just created, keeping other configurations unchanged, and click Create Cluster. We search for the parameters of this cluster and check the value of max connections, which should be 1000. Users can use this feature to define a set of optimized parameters, templates for different applications. besides exporting it as a template. We can also directly apply an existing template in the current environment. Next, let's go back to the first cluster we created. We will introduce access rules, which primarily shows how to enable SSL in databases. SSL TLS mainly provides data transmission security. There are two main ways to enable SSL: generating certificates by the system or providing certificates by the user. The former is suitable for testing and development environments and is easy to configure. Here, we demonstrate generating certificates by the system, selecting a service name as the common name, CN. KubeBlocks will generate a CA certificate, client certificate, and client key, etc. Certificate generated has a quite long expiration time. After enabling SSL, the cluster will restart. Returning to the cluster details page, we can see that the cluster is being restarted. After the restart is completed, applications can access the cluster using SSL mode. The core purpose of a disaster recovery cluster is to quickly switch to the DR cluster when the primary cluster fails, ensuring business continuity and data security in various disaster scenarios. By default, we provide a primary standby mode for disaster recovery clusters. When the primary cluster fails, you can manually switch to the standby cluster. On the disaster recovery page, we click Create Doctor Cluster. Here, we will default to creating a standby cluster with the same version and specifications as the primary cluster. After clicking Create, you'll see it has a label displaying DR cluster, and its status is creating. When creating a doctor cluster, the system will first restore cluster data via backup restoration and then establish the replication relationship. Returning to the cluster list, we can see a plus sign in front of the original cluster. Expanding it will reveal a doctor cluster below, with its status as restoring, indicating it is currently being restored. Clicking this drive cluster will first display its primary cluster information, and its status is restoring. After restoring, we will establish a data synchronization channel to ensure that subsequent changes to the primary cluster are synchronized to the disaster recovery cluster. Let's return to the primary cluster. In basic information, it shows how many disaster recovery clusters the current cluster has. We can choose to promote it to the primary cluster, enter the reason for the switch, and enter its name for confirmation. Its status changes to updating. Here, our processing logic is that when a DR cluster is promoted to a primary cluster, its disaster recovery relationship with the original cluster is terminated. Let's go back to the cluster list page to check. You can see that the plus sign is no longer exists on the original cluster, indicating that their primary standby cluster relationship has been dissolved. We can find records in the switch history, where we previously promoted a cluster to primary, including the reason and whether the result was success or failure. We've covered the main functions of database operations and maintenance. On the home page, you can see multiple menus on the left, allowing you to view cluster lists, parameter lists, backup repositories, and alert information. we can view the list of alerts. Can customize alert rules and configure different alert rules for different engines. In the notification policy, we can create different notification policies. You can also define alert suppression policies. Receiving Group currently provides the ability to push to different IMIS and webhooks, which can be configured as needed. Additionally, we also offer a recycle bin feature. When the recycle bin is enabled, deleted clusters will first go into the recycle bin with a default retention period of 7 days. Clusters in the recycle bin will be in a stopped state, releasing computing resources but retaining storage data for quick recovery. Clusters will only be truly deleted after exceeding the retention period. This feature effectively prevents accidental deletion of clusters. Next, we introduce organization management. A user can join multiple organizations, and information between organizations is isolated. For example, switching to another organization I've joined, you can see that the cluster information is completely different. Here's a MongoDB cluster, and a Redis cluster, some alert messages, and some backup task information, and alarms of different severity levels. Within an organization, we can also invite more members and grant them different roles. Currently, we have 4 types of predefined roles, but users can also add custom roles. Besides that, we also support API access. We can create an API and assign it a valid time. For example, here, we customize a valid time. With the API, users can directly call open APIs to create and manage database clusters. Since KubeBlocks adopts a unified API design, the creation and management processes 4 different engines are similar. Below, we will illustrate with PostgreSQL and Redis. We select PostgreSQL when creating cluster. Choose the desired major version, minor version, specifications. Use default parameter template. Enable automatic full backup and incremental backup. And click Create Cluster. It will take approximately 1 to 2 minutes to create. You can see that the creation and display pages are very similar to MySQL. Therefore, users do not need to learn the creation and management processes of each engine from scratch, which greatly reduces learning curve and complexity. After approximately 1 to 2 minutes, the cluster status changes to running. Similarly, you can perform account creation, database creation, session management, SQL Workbench, for query editor, check metrics, log, audit logs. And backup restore. We can also initiate backup and restore. Configure parameters in the same way of MySQL. And it supports SSL as well. You can also create a disaster recovery cluster for PostgreSQL. These functions are quite similar to MySQL. Next, we demonstrate Redis cluster creation. Redis has more diverse topologies: standalone, replication, Sentinel with replication, and Redis cluster. We'll use replication as an example. Creating a cluster with major version 7.2 and minor version 7.2.7. The replication mode defaults to only 2 replicas. Password credential here refers to specifying the password for the Redis default account during creation. If not specified, KubeBlocks will generate a random password. Similarly, we can also perform some backup configurations and enable PIT. Upon entering the cluster details page, you will see 2 Redis replicas being created, one primary and one secondary. After the cluster is successfully created, its status will change to running. Similarly, we can perform a series of Miska-like operations on it. Since KubeBlocks explicitly defined that replication mode only has 2 replicas, horizontal scaling is not displayed here, but these constraints are configurable. We can also expose services through expose private endpoint and expose public endpoint. We can also see features like metrics, log, backup, and restore. And parameters, operation auditing. As you can see, whether it's PostgreSQL or Redis, our creation and management are very similar thanks to KubeBlocks. Unified API abstraction make things easier. We've covered the user console. Now, let's quickly introduce the core features of the admin console. After logging in, the dashboard you see will be completely different. We can see all clusters, organizations, and environments are present across all environments. Here, we mainly want to introduce the environments management. As we mentioned earlier, each environment is a Kubernetes cluster. We can configure different database engines supported on each environment. Clicking environments, we can add multiple Kubernetes clusters as environments for running databases. They can be deployed in different locations, or even provided by different vendors. Clicking an existing environment, we can see some basic information about it, such as CPU memory and other resources. More importantly, you can enable or disable a list of database engines supported for each environment. You can add different environments for different teams, or add different environments for different use cases, such as a test environment, a development environment, and a production environment. These multiple environments are managed by a unified console. Besides that, we can also configure which object storage to be used. Configure one of the object storage objects as the backup repository. Here you can also customize storage classes. For example, we just used app localhost path as our storage class. You can add more storage classes for platform users to use. Below, in global setting, we configure the engine's display settings, specifications, and other information. Taking MySQL as an example, you can use a JSON file to configure the overview displayed when creating MySQL. Modify resource options, including replicas constraints, specification, configuration, etc. As we mentioned earlier, there are two types of specifications by default: general and exclusive. For example, these are general type specifications, and you can customize the CPU over commit ratio here. Just click Edit to set it. Additionally, we can also see different add-on versions. Since KubeBlocks uses a pluggable add-on mode, each database engine is integrated through the add-on mode, and add-ins also have their own versions. That's all for today's demo. Thanks.